In this video, we are going to talk about the colligative property osmotic pressure. Remember, colligative properties are going to be dependent upon the number of molecules, not their identity. So here is an example showing osmosis. So osmosis is simply the movement of solvent particles through a membrane. A membrane is something that's semi-permeable. And when this happens, we're going to achieve an equilibrium. So what you see on the right-hand side was where if you put a giant container over two beakers, one having a solute and one not having a solute, the solvent particles will evaporate, trying to achieve equilibrium, and then they will recondense down into the solution, therefore making the solute molecules more dilute, but more of the solvent is over on the right-hand side of the figure. Whereas on the left side of the figure, what we have going on here is where we have a solution in green, a pure solvent in blue, and then a membrane shown in brown. And so what happens is it's your solvent that can pass through the membrane, not your solute particles. And so at equilibrium, your volume has once again grown larger because of the movement of solvent from one container through the membrane into the other. So that's osmosis. Osmotic pressure then is going to be related to this osmotic effect. What is osmotic pressure? It's what the pressure that the solution feels, if it could feel, compared to the solvents, and it's simply due to the different liquid levels. So they're trying to reach equilibrium. So look at the blue part of the horseshoe and the green. They're trying to get the tops of those equal. And so in order for these to become equal then, the solvent could go through the membrane. So if the solvent liquid level is higher than the solution, solvent is going to flow through your membrane in order to reach an equilibrium between the two. So osmotic pressure is the pressure you would need to apply to stop osmosis. And so it's going to be dependent upon a lot of things, which I'm not going to go into in detail now, but the idea still is picture it as what pressure do you need to apply onto the solution to stop the solvent from making that transition. Here are the equations for osmotic pressure. So osmotic pressure is the symbol here, and it has units of atmospheres. I is your Van Hoff factor, and that is once again going to be dependent upon the number of particles that the solute dissipates or disassociates into. So if it's sodium chloride, it's expected to be 2, and the observed is a little less than that. Capital M is your molarity. Your R is your gas constant. We want to use the one that has atmospheres in it, and so that's 0.08206 liters times atmosphere per mole Kelvin, where mole and Kelvin are both on the bottom. And then T is your temperature. In order to make it mesh with your gas constant, it needs to be in Kelvin. So the main take home from this is that your solvent is what passes through the membrane, and the pressure is the pressure that would need to be applied to push the solvent back. Dialysis is an example of this. It's a specialized membrane that allows some small solute particles to pass through. So now instead of just allowing the solvent to pass through the membrane, some solute particles pass through. So why is that good? Because now you can let some of the bad particles that are inside of your blood pass through the membrane, thus cycling through, removing the waste, allowing those to come out of solution, and only the good blood returns back into the patient. And so this is a special type of osmosis that allows some solute particles to also move, and that being moving out of the solution and into the solvent that is around the solution. So in the figure here, you can see the small solute particles in blue are going to move out of the solution back into the solvent, whereas the solvent can be moving into the solution, and then other small particles can be moving out. And so you reach kind of an equilibrium, flow in, flow out. And so that's why you might have to do dialysis a couple times, because it doesn't all come out in the first time. And so by running it through again with a new fresh solvent around it, you can get more and more of the impurities out. So why do we need isotonic solutions? So iso is same, so same types of salts. Because if you have too much osmotic pressure on the outside, it's going to want to all come inside the solution. And so that's where you see the swelling on the right. So the solution has a lower osmotic pressure than what's around it. And so that's bad. You don't want your blood to swell. And then shriveling is the opposite, and that's in the middle. That's where you have a much lower osmotic pressure on the outside of the cell, and therefore the higher osmotic pressure on the inside, the solution is going to want to escape. So your solution is going to want to escape, which is going to shrivel your blood cells. And so the idea here is that you got to control that osmotic pressure, or else when you do like a blood transfusion, your blood vessels could pop, and that would be bad. Okay, then we have reverse osmosis. So reverse osmosis is where you actually apply a pressure that's greater than your osmotic pressure, and therefore forcing the solvent molecules to cross through the membrane, but not from the solvent to the solution, but instead from the solution to the pure solvent. And so you're forcing it to go in reverse. And then we have another thing kind of going on here. This is called the Tyndall effect, and this one's fun. So if you take a laser pointer and shine it through the room, you can't necessarily see it. Because the laser pointer, you only see it when it diffracts off of a substance. And so you might see this in movies where they just like spray water, and now you can all of a sudden see the grid that's protecting the bank. It's the same kind of thing. You can do that, and maybe we'll do that in class on Monday. You just spray water, and now the laser pointer will diffract off of those water droplets, and you'll be able to see it. Colloid is simply a suspension of one substance and the other, and so they're kind of suspended. They're not really mixed in, they're not really dissolved. It's just big clumps, if you will, within the solution.